Anti-reflection coating, yes. Texturing, what else? You saw that already, a single anti-reflection layer or several anti-reflection layers of another refractive index. I will first discuss how we can do that in a smart manner. What's the issues we may have, or what's the different solutions. And then you will see that it's not enough, and we'll discuss later how we can further improve light absorption. But that's the first step. I skip this. We've already discussed the solar irradiance spectra that you have here. So I will go quickly through this. The important thing is that in conventional photovoltaics, we have to deal with direct light, but also diffuse light. The sun is moving during the day, so we will need a large acceptance angle. And we have to manage with a large spectral bandwidth. So this is the outline of my talk. We will first deal with anti-reflection coating, then light scattering to increase the optical path in this layer, and other ways to increase light absorption through multi-resonant strategies. And we'll discuss some examples of light trapping in various devices, and we'll see what we have time to discuss. So our first task is to have an efficient anti-reflection coating to suppress light reflection at this interface. So we already said that, the 30% reflection. So what we will use is wave optics. I already said the two important features: large spectral bandwidth, wide acceptance angle. And we have two ways to suppress reflection. The first one is to have a single or several layers to have destructive interference. And the second one is to use nanostructures to have graded indices. So first strategy, a single anti-reflection coating. So you have your substrate here. And the basic idea here is that you have now two interfaces. So you have impinging light. You have a first reflection here. Some light is transmitted, can be reflected here, and actually you can have multiple reflections and path in this layer. But at the end you have an outgoing wave. And if you manage to have the same amplitude for this wave and opposite phases, then you can cancel out completely reflection and you can have zero reflection. So the two conditions to have this destructive interference condition is a condition on the phase that will depend on the thickness of this layer for a particular wavelength, and for the refractive index of this layer, and we have to manage the amplitude of these two waves, and the amplitude is tuned through the refractive index of this layer. So if you have these two conditions, you have zero reflection, and that's what you can see here. You have a reflectance spectra, several reflectance spectra. So reflection as a function of the wavelength. You see as a reference the solar irradiance here, and you see the reflection here with a single layer, and you see zero reflection here. And you see already the issue you have zero reflection at this wavelength, but you have an increase of reflection when you at other wavelength. So that's not the best solution. That's not enough. So what you can do to improve that is to use several layers to gradually decrease the reflection and to have a larger bandwidth through a multi-layer stack to use as an anti-reflection coating. You have to tune the thickness of each layer and the refractive index of each layer. But there is a limited number of materials. And so it's not so easy to have exactly the refractive index you want for each material if you use bulk materials available. So what you can do at least, and what is usually used in conventional solar cells, is to use two layers for this anti-reflection coating. And so you have two examples here, but the interesting comparison is the comparison between the single layer anti-reflection coating. So it's still the reflection here, and what you have with one of the two examples of a double layer anti-reflection coating. So you see a much broader spectral range with reflectivity which is about a few %. So it's not zero, and you can keep in mind that you have, let's say about between a few % up to 5, let's say about 5% of reflection. And as I said, you could do even better with more layers, but you need the right refractive indices. So what you could do is to structure your material. First, you could just structure the material you use for this anti-reflection coating. So from this simple previous scheme, you have the substrate, a single layer, and air. If you use a thicker layer for this material and you structure it, then what you have here is an effective refractive index if the structuration is much smaller than the wavelength. And it means that the refractive index, the effective refractive index of this layer will be in between this one and air. It's the average of the refractive index of air and of this material, and it simply depends on the filling fraction of material of this layer. And so with a single material, you can already have this bilayer anti-reflection coating. And you can even do more. You can change the shape. Instead of square shapes like this, you can use triangular cone shapes, for instance, or more complex shapes. And then in this case, you will have a graded effective index for this layer. And so that's exactly what is explained here. So the idea is to change. So from this, now we change the strategy. Instead of having several layers to have destructive interferences, remember that our main concern is that we have a high contrast of the refractive index between air and the silicon, for instance. We can suppress light reflection by using a graded index to avoid a contrast of the refractive index and to avoid light reflection at this interface. So if these features are much smaller than the wavelength, the material behaves like a macroscopic material, and the refractive index is simply given by the filling fraction of the material. And you can see examples of what can be done. Here I think it's for glass, but we'll see later what can be done with silicon. One question is really a tricky question. What is the better shape for these features? Maybe I can skip this, actually. And I will skip this to save time for more, yeah. So, so we jump from this example for glass to this nice example for silicon. So what you see here is silicon etched. It's etched by a technique based on reactive ionic etching at low temperature, and they end up with these features, which act, so it's not perfectly homogeneous, but it acts as a graded refractive index, so that light never see a high contrast of the refractive index. So they measure the reflectance of this sample, and you can see a reference sample with a single, I think it's a single or bilayer, actually, I don't remember. Let's say conventional anti-reflection coating. And with this feature, the main advantage you can see here is that you don't have this increase of the reflectance at short wavelengths. So it works on a broad spectral range. No. Yes. And they fabricated solar cells. You can see what kind of solar cells you have here. Thank you, IBC, interdigitated back contact solar cells. What's the main issue with this strategy? What's the drawback? Yes.
This strategy is supposed to move the contact from window layer to backside. That can make the window layer just to reset all
Yes.
the radiation. That can lead to increase the current intensity.
Yes, it's difficult to use this strategy with front contact. I think that's what you said first. But there is a drawback of etching the silicon like this. Fragile, yeah. Yes, non-radiative accommodation. You increase a lot the surface of your absorber, and so you can expect an increase of surface recombination. What's the result? Okay, here the results are pretty good. You increase the external quantum efficiency in this region, but finally, due to a decrease at larger wavelengths, probably mainly due to the fact that you etch the silicon. So you lose silicon material as compared to the reference. You lose a bit here, and finally you have nearly the same short circuit current. However, there is an interesting feature as compared to the reference. It's the short circuit current here as a function of the incidence angle. And you see that with this strategy, you have a short circuit current that is nearly constant with the angle of incidence. Up to about 50 or 60 degrees, and that's not the case for simple anti-reflection coating layers. So the conclusion for this first part is that with double layer anti-reflection coating, you have good results in this wavelength range. However, to do these anti-reflection coatings, you can make use of transparent conducting oxide layers, which will act as an optical. They will have both an optical and an electrical role, and you can have even lower reflectance using this kind of IDs like graded refractive index coating and nanostructurations. And you have also with this strategy wider angular response. So now what you have? Let's imagine we have a perfect anti-reflection coating. So all the incident light enters into your material, your absorber. But if you have no reflection at the backside, then you have a single pass absorption. So you have an exponential decay, and the absorption can be written with this Beer-Lambert law. It's simply an exponential decay with d the thickness and alpha the absorption coefficient, which depends on the wavelength and of the imaginary part of the refractive index. Then you can do better. You can add a back mirror, and then you will have a double pass absorption, and it's the same equation with a factor 2. And now, maybe it's not enough. We want to do better. So what can we do? We are at this point, if we have a perfect anti-reflection coating, a perfect mirror, we have a double pass absorption and no more. After a double pass, everything goes out because of the reciprocity principle. You have the same transmission here and here. Yes. So why? Texture, yes. To scatter light. Yes. A higher light path. And what do you think is important to have a longer light path? Sorry?
Better absorption of infrared.
What do you need to have a longer light path? Yes, change the angle of propagation. And do you think it's the main factor that will
More reflection.
Yes. But I said, okay, there is a reciprocity principle. So the transmission on one side is the same as the transmission on the other side.
For the same angle.
Yes, exactly. So we have all the ingredients for the following steps. Light scattering. So why? Okay, for silicon, we already saw this. It's the absorption depth. It's the inverse of the absorption coefficient that I have shown previously. So that explains, but Uwe already presented that if I remember well. It explains why you need at least 100 microns and even more if you want to absorb in this light in this wavelength range if you have a single pass absorption. So you want to improve that. So it's particularly relevant for silicon, which is an indirect band gap semiconductor. So the strategy will be this one. So you have incoming light. Imagine you have an anti-reflection coating, so no reflection at this point. Normal incidence, and then you have light scattering at the backside, for instance. So you will change the angle of propagation of light, but if, as you know, at a certain angle of incidence, you have a perfect, a total internal reflection at this interface between a high refractive index and a low refractive index. So if light is scattered in the what is called the escape cone, then it will escape. If it's scattered outside this escape cone, then you will have total internal reflection. So in this case, you will increase the light path because this travel is longer than the one at normal incidence, but also because you have total internal reflection, and so you can make another turn and another path in the cell. So how to play with this and how to try to model a bit this. So how to do this in conventional solar cell, it was already said. You etch with KOH, for instance, and maybe some additives, and you can have this kind of random textures. I'm not sure you have the optimal, we'll see that very soon, Lambertian scattering feature, but you have light scattering with these shapes. And an important point, the scattering can event can be at the front side or at the back side. It's exactly the same. The theory of this strategy has been first developed by Yabnunovich in the 80s. He made the following assumption. Your absorber is in thermodynamic equilibrium with the black body radiation. You have a perfect mirror at the back side. You have an ergodic behavior of light rays. It means you can say that you lose the phase of light between the back side and the front side and the back side. It means that you will have no interference features. And he made the assumption that you have Lambertian scattering, and he derived a theory to show that the maximum absorption enhancement factor is 4n squared in the case of, as compared to single pass absorption. In the case of low absorption, if you have weak absorption, and for thick solar cells, because you are in the ray optics paradigm. And he have shown that the absorption can be written with this formula, alpha d over alpha d plus 1 over f, or where f is the path enhancement factor. I propose to show you how you can derive the same result, but with a slightly different demonstration. So we keep the same assumptions, and what we will do is a balance of photons in your cells. So here I follow the similar demonstration that you can find in this paper. Here you have a perfect anti-reflection coating, you have scattering events at the front side, and you have a back mirror. You have incident light here. So if you have incident light here, you have transmission. You have then you will have light absorption and light traveling in the cell. You will have light back in this direction and eventually reflection. So we first write this guy as a function of incident light and the flux you have here. So it's flux of photons and as a function of the reflection coefficient here and here. So here you have the incident flux multiplied by 1 minus the reflection, and you have the flux in this direction, upward flux, multiplied by this reflection coefficient. Okay? Okay? Thank you. Second, here you have a mirror. Okay, at this stage I don't know if it's a perfect mirror or not. So light here travel here, is attenuated through absorption, is reflected and comes back and is still attenuated through reflection. So you have this attenuation factor. So this guy is equal to this guy with the attenuation factor multiplied by the reflection coefficient. Okay? Thank you. Last stage, you have to write the light going out, which is incident light with this reflection coefficient. Okay, I said you have a perfect anti-reflection coating, but we will add this assumption later. Okay, so reflection coefficient plus what is going here multiplied by 1 minus the reflection coefficient. Okay. You can solve these three equations. It's not a big deal. The absorption is equal to 1 minus the reflection normalized by the incident light. And you can solve these three equations, and you find this expression with the absorption, which depends on, obviously, the absorption coefficient, the thickness. It's an effective thickness here. I will explain that later. I can say now. It's the effective thickness of light. Actually, we will deal with an average of the photons here at an average angle, and that's why we have an effective thickness and the different reflection coefficients. So let's play a bit with this equation. We said we would like to have a perfect anti-reflection coating, so this coefficient is 0. Perfect back mirror, this coefficient is 1. And this reflection coefficient is exactly what you said. You want to have a reflection of light that are scattered and that are photons that are at a certain angle of incidence coming back to the front interface. We can define a probability to escape, and it's 1 minus this reflection coefficient. Now, if you take all this assumption and if you assume that alpha d is small, so you come back in the case of weak absorbing material, as Jablonovich did, then you can make a few approximations and find exactly, there is a mistake here, it's a plus, exactly the same equation that previously. And the optical path enhancement factor F can be expressed as the effective thickness of these average photons that travel from one side to the other, and the probability of photons to escape when they reach the front interface. So this probability to escape can be expressed using the escape cone and the solid angle of the escape cone. I think Daniel wants to discuss about solid angles on Friday morning. So you will be able to explain that if you want. It's not a big deal. So yes, you have this if you make the following assumption, Lambertian scattering. So here I write, at this stage, I write the solution if you imagine you have Lambertian scattering. What does Lambertian scattering means? It means that after scattering, you have an equal probability to find photons in every directions. Okay? And if you have this probability, then you will find once again the explanation of this is very easy in this paper. The effective thickness is twice the real thickness. And so with this angular distribution, the Lambertian angular distribution of photons, you find this average thickness, effective thickness, and the probability of photons to escape. And finally, this 4n square number. And you see that, okay, 4n square, it's about 50, okay? But what you see is that you have a factor of 2 related to the back mirror, because we have a perfect back mirror. So this is the double pass absorption, okay? We have a factor of 2 because light propagates at certain angle, which is no more the normal incidence, okay? At average, it's the light path is twice the thickness. And most of the effect of light trapping comes from the total internal reflection of a large part of the photons. Yes?
Just jump in because you also tried that paper and just before another generation of PV researchers believes that the Jablonovich limit Lambertian situation. That's definitely not the case. So the Lambertian, so as you nicely described, the Lambertian scatterer is one example of getting to those 4n squared. In principle, it's even the worst example. But so in many papers it's written we are close to the Lambertian limit, and that's not a limit. It's an example for the 4n square situation. But one can put very simple. If you operate junction as a light emitting diode, well, you generate light inside. And all for the very weak absorption case. And all of that light somehow gets out of the device. There is, after scattering force effect, eventually that light generated internally gets out. In all that's done, and you can figure out there are thousands of ways how to manage it. Then, if you just by reciprocity turn it around, this device fulfills the 4n square requirement. That's because the 4n square is the average light path. So one example would be if you just have a wafer with you need anti-reflective coating to avoid the reflection, but it's still flat. So if it's flat, you're getting only light in, light out. So that's only factor 2 with the reflection. So then you make a little tiny scratch on that wafer. That already is 4n squared. So that's worse than Lambertian, but it will be 4n squared because you have very short light passes all going in and out, but the one light path that hits the scratch and gets reflected more or less gets infinitely long and will give you the 4n square average.
If alpha d goes to 0. If alpha d
So
goes
it's
to
really
0.
in the very extreme limit.
Yes, yes.
But
I agree, and as we already discussed and you already pointed out, it's not a limit.
Lambertian is not a limit. Jablonowicz is a limit
For
the very weak absorption.
exactly.
Yeah, that's just because there's so many papers that use the term Lambertian limit, and that's a Lambertian case, not a limit. Please remember that, whatever you're doing.
And so that's why a few years ago, the title of this slide was
Okay. Okay, sorry that
was what was it? Light trapping limits, and now it's reference models.
that's
But you remember I made this mistake 2 years ago. But listen carefully to the following of my talk, because I kept the historical reference challenge in the following slides. So to come back to this, this absorption and this 4n square, yes, is may be seen as a limit in the very low absorption range, but nobody demonstrated that it's a limit elsewhere, and we even demonstrated that you can do better. And I will show you how we can do better later. So it's not a limit. It's so now we have three reference models. This is a limit if you have anti-reflection coating at the front side and at the back side. But okay, it's single pass absorption, double pass absorption if you have a perfect mirror. And if you have Lambertian scattering, you can have this kind of optical path enhancement factor. But definitely it's not a theoretical limit. And I wrote here it's valid, what I said is valid only in the weak absorption regime. Yes, and once again, the reason why I like this to show how to get this formula like this is that you see explicitly that you have a factor of 2 related to the double pass, a factor of 2 related to oblique angles, and a factor of n squared related to total internal reflection. Let's go on.
Excuse me, can I
Yeah.
ask a question?
Yeah, sure.
So you're assuming that the material for this application shouldn't have a very good absorption, right? This assumption is based on mathematical derivation, or it will affect, like a good absorption would affect the cell performance.
I assume you have weak absorption just to derive the last formula. But what I want to say, and I will show you examples later, is that you can use light trapping to decrease the thickness, but you actually, light trapping is useful for any thickness and any absorption you may have. You always want to increase the absorption. So whatever the absorption coefficient, finally. I don't know if I answer your question.
Good absorption material won't affect this technique.
Okay, if you have very good absorption, maybe you don't need to increase by a factor of 50 the light path, obviously. It's not the point. So if you look at direct band gap semiconductors, you have a much lower absorption depth, and you can see that in the visible range, you have absorption depth in, let's say, below 1 micron. And so it also means that you cannot use simply ray optics, and you need other tools. You need wave optics and even nanophotonics concepts. Just an example of what you can calculate is the absorption in CIGS. You can have the same with any other direct band gap semiconductors. If you have 2 microns, you have a nice absorption spectrum and high absorption close to the band gap. And if you decrease the thickness, you decrease the absorption, in particular close to the band gap, but for thicknesses down to 500 nanometers, for instance, you see a drop of absorption. And in this case, you may want to increase the absorption using light trapping techniques. What I want to discuss here is the use of periodical patterns instead of random scattering. So if you have periodical patterns, you may have different optical phenomena. If you have very small features, as we already discussed previously, you have an effective medium. You have simply an effective medium with an effective refractive index. If you have features of the order of the size of the wavelength, you may have resonances. I won't explain too much this. But if you have periods of the order of the wavelength or slightly larger, then you have diffracted waves. And we will use these kind of features in the following. You can calculate the angle of these diffracted waves using the wave vector in the plane, so which is written here, and which is the wave vector of incident light. So at normal incidence, you have 0 here, plus 2 pi over p. P is the period of the grating multiplied by an integer. Okay? So you have diffracted waves at different angles. And we can use this kind of diffraction effects to trap light in solar cells using periodical features. And with no solar cells, actually, diffraction was an effect studied a few years ago. So it's for the challenge of the historical papers that you should read. And actually, I have to say that I read this paper very early during my PhD. And it's a very nice paper. So let's read a bit. The title, on a remarkable case of uneven distribution of light in a diffraction grating spectrum. And what you see here is a photograph of diffraction light, so light diffracted by a metallic grating. So you have here something like that. Maybe the grooves are not as square as I show here. You have a metal. Actually, I don't know. I don't remember which metal is in this case. Later, we will consider silver metals because you don't absorb too much in silver. You have an incident light, which is varied here. So you see different angles of incidence. And they look at the spectrum, the reflected spectrum. And Wood saw these features, which are really remarkable, because he saw that you have a jump of the diffracted intensity. You see the dark shape here and the white shape here. So I want to jump to the, so he discussed these measurements, and I want to show you, just for fun, the end of the article. So it's the very end of the article. So the study of this grating has been limited to the 2 or 3 days immediately preceding the closing of the laboratory for the summer. So there are very limited data because it was time for vacancy. So actually there is only this photograph that I have shown. It was sent on June the 2nd, and as you can see, it was read at the Physical Society only 18 days later. And I guess you want to read more articles like this, so you have some references here. No, just an interesting point. Rayleigh, only 5 years later, explained exactly what I explained here, so this formula. How to find the angles of diffraction. As he said, okay, it's simply a diffraction effect, but it was not, because what you see here is that you have, and that's why it was remarkable, you have some peculiar shape here. You have a decrease of light here, and here a sharp event. And so it's something like this. The spectrum are like this. What is it? A resonance? What kind of resonance? It's a phonoresonance. And so Rayleigh explained that. Then Wood continued to study these kind of gratings. And Fano explained that it was a resonance phenomenon. That is a phonoresonance. That is a very general type of resonance. Okay, now I have to speed up with this historical. So what happened in this? Why do you have a resonance? Actually, what he observed is that you have absorption in these metallic gratings, and these resonances are related, it was explained later, it's related to surface plasmon resonances, so waveguides, guided waves at the interface between the metal and the air. And what we are interested in here is to have also guided mode resonance through diffraction effect, but waves trapped in the absorber, as it's shown here, or in a more nanophotonic picture, diffracted light coupled to waveguide modes, so that light will travel in this direction, and that will increase the absorption. So finally, this is very similar to the scheme of Wood 120 years ago. So we already always use past phenomena. The main difference is that here the absorption is in the metal, and guided waves are surface waves. But I will show you how we can. I have to speed up, that we can use the same kind of phenomena to increase absorption in absorbers. Actually, the point is that the strategy is, so if you have this kind of features, you have resonances. I have shown would have final resonances. We will play with Lorentzian resonances, and the main idea behind this kind of resonances is to have a diffraction effect. You have resonances due to these waveguide modes, and if you have a lot of resonances close to each other and overlapping between the resonances, then you can have a large enhancement of the absorption and finally high absorption and broad absorption. And the number of resonances depends on the period of the grating, of the number of diffracted orders, or on the density of optical state. So I skip this. So this is another strategy as compared to Lambertian. You can write equations. We won't do it. Yes, I want just to show you, just look at this graph. You take the refractive index of crystalline silicon. You say, okay, I have 1 micron thick silicon. I plot single pass absorption. You have this curve. Lambertian scattering with the formula I have shown, you have this curve. Remember, this formula is not correct in this region, but you can play with it. And if you have multiple resonances, you can have even higher absorption. If you have an absorption spectrum like this, you can integrate the absorption multiplied by the irradiance spectrum of the sun, and if this absorption is equal to the external quantum efficiency, you will have the short circuit current. So if you assume all photogenerated charges will be collected, then you can have the expected absorption from these kind of calculations. And so you can plot the short circuit current you calculate as a function of the thickness with these different models, so single pass absorption, Lambertian scattering, or even multi-resonant absorption. What you see is that if you look at the short circuit current you have at 1 micron, you see that you could have the same short circuit current with much thinner, actually 50 times thinner about absorbers if you are able to use light trapping and efficient light trapping. Before showing you examples of ultra-thin solar cells, I just want to show you that you can play with these different tricks. For instance, you can create, on conventional solar cells, you can create pyramids, random pyramids. You can add nanostructuration. You see it's not the same scale, 5 microns here, 1 micron here, so very small features. And you can add this feature to this one and have this kind of structures. And in this paper, they compared pyramid and pyramid with these features. What happens? Just look at this. External quantum efficiency for the two for the two samples. The reference, you have a very conventional external quantum efficiency of a good solar cell here. And with these nanostructures, you decrease the reflectivity in the short wavelength range, and you increase the external quantum efficiency. However, you decrease a bit the collection efficiency in this part, and so finally the efficiency is very similar. But you see that you can play with this and potentially further improve the absorption as compared to conventional solar cells. Another example, so now let's discuss just a bit of multi-junction solar cells. I like this example because it shows you an example of a typical high efficiency multi-junction solar cell made of 2 3-5 junctions bonded on a silicon cell. So from the optical point of view, obviously you need a good anti-reflection coating, but then you have no high refractive index contrast because the refractive index of 3.5 is close to the refractive index of silicon. I think it's not in your slides, in your booklet. Don't look for it. What's the issue here? So it's a two-terminal. You have the same current from the top to the bottom. And you have a nice efficiency, 31.4%. And you have the external quantum efficiency of each cell here. So the top one, the middle one, the third one. And you can measure the external quantum efficiency separately of each cell. And you have the integration of this external quantum efficiency. So the short circuit current you may have for each single cell. You see, what is the weak cell? Yeah, the bottom cell. You see, you are finally limited by the current of this bottom cell, and that's what you have as a current for the whole free junction cells. What they did is they took exactly the same cell, they removed the back contact, and they added a pattern, so a periodical structure to have diffraction effect. You see the diffraction in air here. That's the reason for these nice features. And you see the effect on the bottom cell of the diffracted grating. So it's reversed here. So you see the bottom cell here and a silver mirror with a pattern here. And what you see here is the external quantum efficiency before and after this nanostructured mirror. And you see the improvement. So due to diffraction effects and light trapping in this bottom cell. And finally, the increase of the short circuit current makes a very good current matching between the three cells. So light trapping can be used in thick conventional cells or in multi-junction cells. It can also be used to decrease the thickness of solar cells without losing short circuit current. I will go very quickly through this because I don't know who is the timekeeper. Maybe it's me. Okay, it's me. I will manage that. So I show you very quickly what we did with Andrea and with Ines. So Andrea, maybe you can leave me a few minutes to show the work you did also. So short circuit current as a function of the thickness for crystalline silicon. Okay? You have 4 different reference models: single pass absorption, double pass absorption, what you expect if you have Lambertian scattering with 4n square, and what we calculated in another theoretical framework here as what we think the upper bound for absorption using multi-resonant light scattering. What you see here is a result from the literature for numerical work. So just calculations of absorption using different features. And you see some of the points are above the Lambertian model. So that's not a limit. So this is an example using periodical structures with some fancy cone-shaped voids in silicon. And you see the absorption spectrum above the Lambertian K model and not limit. It's written limit, but I didn't write it. Other examples still significantly above the Lambertian model. And many other examples. Mainly the issue is that in most of these cases, they did calculations without taking into account all the window layers and the parasitic absorption you can have everywhere in your cell. So it's idealized devices. And now this is the experimental results we have found in the literature. What do you see? far below, and very close. Nearly all the results are very close to the single pass absorption model. All this work to arrive here. 3 points, no, more than 3. You have this one also, but in this range, 3 points only above the double pass absorption. Why? Because you have a lot of parasitic absorption everywhere. Because your anti-reflection coating is not perfect. Because most of these cells don't have a very good back mirror. So your first task is to have a good anti-reflection coating and a good back mirror before using these fancy light trapping strategies. So they succeeded in this example to have a very, very nice short circuit current as compared to the other examples, using an aluminum back mirror and inverted pyramids, regular pyramids here. We did this work on only 3 micron thick devices. And there is I skip this quickly, but I will tell you just a few words on this. And another example for really very thin absorbers. So message, plenty room for improvement if you want to play on this. That's the example we did. So it's kind of inverted pyramids. I don't enter into the detail on the technological part. We transferred a 3 micron thick silicon layer. It's PECVD silicon, so it's AP silicon, but it's not perfectly crystalline as you see usually in the cell. And what you see here is external quantum efficiency with no texturation in blue. So you have double pass absorption. Double pass absorption in green is what you expect, so you are close to this. And if you add these inverted pyramids, you have this external quantum efficiency and a nice improvement of the short circuit current thanks to these diffraction events. And we have shown that you can fit this part of the external quantum efficiency with this model that you have seen and find that we have a field enhancement factor of 10. So it's feasible to improve, to have light trapping effects and to have an enhancement factor of 10. We have, yes, that's interesting. The external quantum efficiency we have measured and the calculations that have been done with the INL laboratory. And so you see all the losses. So, okay, we have a field enhancement factor, a factor enhancement, path enhancement of 10, but we still have a lot of losses. We have reflection losses, no absorption here. But to make all the cell, we have used ITO. Top passivation, I think it was amorphous silicon. And zinc oxide at the bottom between the silicon and the silver back mirror. And so you see that all these layers induce parasitic absorption. And if you increase the optical path by a factor of 10, you also increase parasitic absorption. Imagine you have a 10 path of light here, and actually here you have some parasitic absorption in the layers. So you see these layers, the photons see these layers several times, and so you absorb more, you have more parasitic absorption than in the same structure with a single pass absorption. And so finally, that's why most of current solar cells are far from the limits because of this parasitic absorption. And you can find very similar features for other more conventional solar cells. And I will end with wood. So this is exactly the same benchmark for gallium arsenide. And I just want to show you, I can't resist to show you what we did and what we published last year. So we took the wood nanostructured grating, metallic grating here, at the backside of a gallium arsenide solar cell. And this grating allows to couple incident light into waveguide modes here. We optimized everything. We fabricated these cells in collaboration with Fraunhofer Ise and the team of Frank Dimroth. And we used only 200 nanometer thick gallium arsenide as compared to about 1 and 2 microns for conventional gallium arsenide solar cells. And we have shown that we can have in red very nice external quantum efficiency as compared to a flat back mirror or no mirror at all. You see the improvement here in very nice agreement with what you can calculate. Here you see dispersion features very similar to wood dispersion features, the function of the incidence angle. And finally, we had a certified 20% efficiency with this cell. And it's not written, it was published in Nature Energy. Well, it's written here. So the timekeeper says that I should not use privilege and I should stop. So let's go to the take-home messages. Maybe the most important is first to have a good anti-reflection coating. Then, second important thing, if you want to have high GSC, to have a good mirror. And if you look at all the crystalline silicon solar cells you have seen this morning, most of them don't have really good back mirror. And then you can play with light scattering or periodical structures to further enhance light. And in most current devices, you are really far from what you could do and far from the limits. And probably Friday morning, Daniel, once again, or Jean-François, I don't know, will also speak about other optical aspects like concentration. And for sure, after the break, Laurent will also deal with emission of light and luminescence, which are also optical stuffs. I have to stop. Thank you. But we may take just a few short questions. Yes?
So you're saying that it's better to have a reflective back surface. What about albedo? How does that...
Good question. The issue that you have is that we have seen that there is an escape cone. So light in the cell will escape only if it travels at an angle in the escape cone. It's the same, as I said, you have a reciprocity principle. And so if the mirror is on the high index material, then you have total reflection. But if you have air here, for instance, if you have light scattering with an air gap, then most of the light scattered will arrive at some angles and won't enter into the cell. And albedo is far from 1. Indeed. Yeah.
I wanted to know if it was possible to play a bit with this grating, but not on the backside, but on the top layer.
Yes, sure. So you can do exactly the same, but there is a trick. The trick is the following. To have diffraction, I can write it here. To have diffraction waves, you need a period larger than the wavelength. So if you have a periodical structure here, you will induce diffraction, a period greater than the wavelength divided by n. I hope I make no mistake. And so you will have diffracted waves here, but you may also have diffracted waves in the air here. Okay? So you have to tune the period to have diffracted waves in the high index region, medium, and not in the air. And it's much easier to do that at the backside because you only deal with photons that are not absorbed on a double pass absorption. So most of the examples, I have skipped some slides where you have examples of people using, and it's actually it's also what you did when you use periodical inverted pyramids on the front side. You have diffraction effects, but to my point of view, it's better to do these tricks at the back side to avoid, in a certain extent, to avoid diffraction in air. Laurent, do you want a coffee? Yeah. It's time for the break.
Excusez-moi.
Ouais.
En fait, c'est une figure comme ça. Non, ça c'est le JSC.
Ouais.
Je voulais avoir pareil en fait pour le EQE.